Right, good afternoon, and I welcome you to this session on human factors. My name is Dirk Schaefer. I work at the Eurocontrol Innovation Hub in Brittany. I'm also the program chair of the SESAR Innovation Days. We have 4 speakers in the session this afternoon. 2 presentations will be given about speech recognition, and they are both from DLR, Hartmut Helmke and Matthias Kleinert. We will then have a short coffee break of 10 minutes or so, and then we have 2 more presentations by Tiago Nunes and Yash Guleria, and those two presentations are concerned with strategic conformance, which is an interesting concept and something that I'm sure Tiago and Yash will do a great job explaining to you. We then have one, I believe, poster teaser, and then close the session right in time for the SESAR quiz that will take place, I think, at 5:15. So without further ado, I'd like to introduce the first speaker, Hartmut Helmke from DLR. Hartmut has been at DLR Institute of Flight Guns for as long as I can think. He was already there when I was a PhD student there many years ago. And over the past 10 or so years, he's been working on speech recognition, gradually nibbling away all the little problems that are the little obstacles to introducing speech recognition in ATM. And I look forward to his presentation. Hartmut is project leader of a project called Hawaii, which is slightly misspelled. Before that, he was project leader of a project called Mallorca, which was also misspelled. And I think Hartmut owes us an explanation why Hawaii is misspelled. Hartmut, the floor is yours.
Thank you very much, Dirk, for this kind introduction. Okay, I will try to give you why it's misspelled, but that's you can ask in the question and answer session, though otherwise it's lost from my time. So I'm a little bit talking about speech recognition today, but mostly on speech understanding. What that should mean, yeah, well, you should see here, I got a motivation from some of our reviewers who asks the question, what accuracy do we need for safely introduce speech recognition into the air traffic management system? Well, and I fear I have to answer, yellow accuracy is enough, but pink might be not enough. Okay, if you're listening, that might be a very useless answer, but I fear currently we are not able to give better answers because we cannot quantify the performance of speech recognition applications in the air traffic management domain. And I will try and answer, though what I will try is if you have just 2 speech recognition applications available, you want to evaluate which one to buy. Well, let's really be honest. Which one we should use as a starting point for improvement. I would say currently all the things you can buy on the market are not really ready to use immediately. Though, yeah, that's my talk. Not only speech recognition, but also speech understanding. Yeah, and here are all my co-authors, which you see, thanks again to them. Though, yeah, I will talk a little bit about the building blocks, then a little bit requirements beyond just famous known word error rates to give a new metric and have some results. And of course, at the end, we will have some conclusions. Yeah, though, if you're looking at the building blocks, yeah, well, you have a wave signal, you have the speech signal, and you have a sequence of words. Yeah, coming from, for example, an air traffic controller or from the pilot. And well, the next step, if you want to understand something, well, you have to extract, recognize the important concepts. And in our part of speech recognition in the ATC domain, we're talking about call signs. We're talking some types. Yeah, we have here 2 concepts extracted, the reduce, the descend, and we have some values. And well, furthermore, a concept 10 years ago, DLR and Saarland University have introduced is a so-called assistant-based speech recognition, which relies also on the concept prediction, where we try to predict which call signs are in the air and which concepts the ATC might tell in the near future to the pilot. Yeah, there are some requirements. There, if we are looking here on this example, which might an ATC say, or good morning, speedbird 220 alpha, we use 180 knots under DMA 4 miles, contact tower on frequency 118.0 8700. Compared to ATCO, I'm not speaking first, and the pilot might say something like 180 to DME4, Tower 187, speedbird 2000 alpha. And now the interesting question is this a readback error? Semantically, are they saying the same? I'm not talking about if it's a good readback. I'm talking about, is that the same? And you have already seen, well, it's a correct readback, but the words are here completely different. And not every command, of course, doesn't need a readback. So it must be repeated by the pilot. And the commands in which the pilot can repeat it might be different. You also have seen the pilot says 18, and the ATCO a little bit more better says 118, and one says 1000, the other says 000. Yeah, and you might see here already what Alan Turing has already observed 69 years ago. Yeah? He says speech recognition is completely different from speech understanding. Yeah, you have to go a lot of steps. Yeah? And yeah, what we want is we want to come here from the sequence of words to the so-called concepts. Yeah, though we need an algorithm for language understanding for transforming the words to semantics. Okay, this algorithm we have already presented on other conferences. Though what we need, however, first, before we have this algorithm, is we need to agree on the output format, which is mostly done already on word level. So if you're talking here about, I think the output format is very clear. Yeah, maybe you can write everything in small letters, or you are writing 9 and not 9er, and all these things that are agreed. But how should be the output on semantic level? That's a question. And 3 years ago, 22 partners from a lot of European countries in the air traffic domain have agreed on a so-called ontology. So we agreed on that the ATCO or pilot instruction utterance consists of multiple instructions, and each of these instructions might contain of a call sign, the speaker, the type, the value. And if you're looking here on this example, this semantically could be something like this. And well, we have here the call sign. This we will call the type. Here you see the value of the type. You might have a unit, and you have here some conditions maybe, or you have no conditions or multiple. So that was agreed. And with this, we really come to a little bit quantifiable. Though with this, we can really compare speech recognition applications. Yeah. If we, for example, see this, if we want to have on semantic level this as an output, yeah, we say that a speech understanding system has recognized this correctly if the call sign is correct, if the type is correct, maybe the second type, the value is correct, the unit, the qualifier, the condition, so everything must be correct. Otherwise, we say it's a recognition error, or at least we say it's a rejection. Yeah, let's compare it that we want. And if we get this, a wrong value, we say it's an error. Well, if we get this, no call sign is recognized, well, then we talk about it should be a rejection. We call it an error, it's just rejected because no harm. Yeah, if we get no output, we also say it's a rejection. But yeah, if two errors are recognized on semantic level, it's just one error. We only compare command instruction by instruction. Well, if in a condition just one part is wrong, it's a full error. Or if we introduce something which is not set or above the qualifier, we also say, it's an error, just one error. So what we are always doing, we are transforming this output into a big word. We are comparing this, transforming this into a big word, and then we call just the difference on this big word levels. Yeah? So speech recognition people call this calculating the Levenstein distance. So with this, we can now define the new matrix, the command recognition rate, which just means, let's call on semantic level the correct matches divided by the number of instructions which we have. Yeah, though the good ones by all ones. Okay, I think that's the definition. Yeah, we also can a little bit have the error rates, the command recognition error rates, which are just the wrong ones. So the ones which are wrongly recognized, a descent by a reduced recognized, or the substitutions, plus the commands which were recognized but which were never given. And well, the rejection rate we define as the commands which are, well, were given, but which were not recognized at all. So not wrongly, just no output was generated. So, and the same we can do if we just focus on the call signs. Now we can then have a call sign recognition rate. We can a call sign recognition rate. We can have a call sign error rate, and so on. An example might a little bit help to understand that we want the left part, the right part. Maybe we get this. Green ones are correct. Purple ones are completely wrong, and the yellow ones, well, there we talk about a rejection. And well, if you compare this, we would come to an error rate of 50%, something like that. The recognition rate of 50%, the error rate here also 50%. Yeah, and if you zoom up all three, yeah, it's easy. You see it's more than 100%. And this just could happen because more could be recognized than that was even said. So if 4 should be recognized, but you have 5 wrong ones, well, then the error rate is more than 100%. But this is just in the theory. If you have real examples of one day of recognitions, you normally have a sum of 101% or something like that. Yeah, some results using this. Yeah, well, we observed here from the Mallorca project, just written with one L, from the ops room data of Prague, from laboratory, which we had some recordings from the 1604 project together done with Thales, from the ops room of Vienna, from the laboratory of Vienna, and you see, well, that's the number of utterances which you have, the number of commands. So in most utterances, on average, you have 2 commands, but you could even have 7 commands. Yeah, and if you are looking here on the extraction rates, recognition rates, yeah, it's 98% or it's not 95%. The error rates are in this area, which we did with our algorithm. If you're looking on the call sign rates, they are quite good to say. But now let's be honest. I have talked about the perfect speech recognizer. Yeah, if we have a word error rate just of 0%, how good was the extraction algorithm then? And that's even not perfect. So at least in our implementation. Yeah, if we have a real speech recognizer with the data of the Prague, Mallorca, well, there we had an error rate of 2.3%, and there we got recognition rate on the command level still of above 95%. Call signs are nearly 99%. If we are already providing the information with call signs are in the error, the error rate for the words goes up. If we are using here, we have here what we call a bad model. We trained our models just on one speaker only, and we try to recognize all the other Prague speakers. Well, then the word error rate, of course, goes up, but the recognition rate, the extraction rate is not so bad. Right? It's, of course, not so good. It's better to have to train on more ones. Having the same on Vienna, okay, you see the perfect one. We still have the problems on recognizing really all the phraseology deviations from Vienna. And if you have real speech recognizer with a rare word error rate of 5%, 90% are achieved. And if you have the bad models, you still achieve 82%. So I think the algorithm works, and the definition of these rates, it's also quite usable. If you're looking on another application, which is more the Hawaii application at the moment now, where we try to do readback error detection. And there we also have to recognize the pilots. And if we have here now, here I have noted in the rows the possible recognition rates versus the error rates. Let's assume, for example, if we have a recognition rate of 75% and an error rate, let's assume of 0.5%, then here you find the false alarm rate of this readback error detection assistant. Though with 75% and a nearly perfect error rate of 0.5%, which is really, really hard to achieve, you still get 25% of false alarms. So if you have readback error detection assistant, every 4th output is a false alarm, which might be still good. Yeah, but here you see it's really challenging to achieve that. So yeah, I think command recognition rates for this application, 50% should be enough. But error rates, yeah, you need to be very, very good. Let me conclude to the end. Although what we have shown is that the ontology, which was developed in the SESAR project, is now also updated for pilots. And well, we have now an implementation. We have it not only on paper, but we can really transform into this ontology already with an accuracy of 95% automatically, for some applications even better. And well, it's even robust, the application, against if you have a real speech recognizer with a lot of errors in it. And well, be honest, I have not introduced a new metric with this new command recognition rate. Yeah, what I have shown that the definition of this gold annotation itself, I think that's new. Yeah, that we now agree. Well, okay, for 3 years now we have it. We have agreed on what should be the output, and what I have also maybe shown the word error rate. If you just look on the word error rate, how good the speech recognizer is, you cannot measure how good your application will be. Yeah, you have to look on the application level. Yeah, at least on the semantics. I've also shown examples where you have a good word error rate, but at the output is not so good. So to answer maybe our reviewer, if he is in the audience, I would say command recognition rates of 90% if you want to do radar label maintenance, yeah, are fully adequate, and that's also the output of the ATCOs, which will participate in our trials. Well, that's not perfect, but that saves a lot of the workload. Yeah, that saves 2/3 of their time that they are using for clicking. So, and if you're talking about the readback error detection assistant, well, I would say then you need command recognition error rates of below than 1% to achieve the false alarm rate. Okay, I think I was nearly in time. Dirk, thank you very much for your attention.
You were indeed perfectly in time. You're 2 minutes late because I was talking for 2 minutes when I introduced you. I don't see any questions in the Q&A box. That might be because I haven't refreshed my screen. It might be there on. In which case I would use my privilege as session chair to ask a few questions. Now, you said the readback error, even with very low word error rates, you would come to false alarm rates which are 25% or so. And that does that mean this is probably the last application that we will actually see happening, or do you have experience from your experiments that these 25% false error rates are actually acceptable?
Well, I think, first of all, sorry, Dirk, that I am correcting you. You talked about word error rate. I said nothing about word error rate. Word error rates are completely useless. If the good morning is not recognized, it does not matter. Yeah, though we are talking on the command level, really on the semantic level. There we need this perfect rates, not on the word level. I think that we maybe will never achieve. Yes, I think the readback error detection assistant might be the king's discipline, the hardest application. On the other hand, well, we can run it offline. You can do that without any safety issues. Maybe you just input all the data of one day and you get an output, or how many false alarms there might, or how many readback errors there are. So it's not safety critical. I think we can do it. But well, yeah, well, the ATCOs told us for the Hawaii we have the requirement the false alarm rate should be below 10%. On the other hand, currently what we are achieving, if you're evaluating the data, we have 2% of the cases roughly contain readback errors, and 50% of this are recognized by the ATCOs, not more. Although I think this readback error detection assistant, I think with 25% might really be already helpful. So if we can get rid of one accident by readback error detection, I think everything is worse.
I think I agree. I read in a very old study that controllers typically pick up about half of the readback errors, not more. So if you have a 25% error rate, this is still a helpful system. You're kind of leading the way into the next question I wanted to ask, and this is about, you said that now the readback error detection is probably the hardest chunk. What are the easiest applications? Where will we actually see, not in training, but in real life air traffic control, where will we first see speech recognition happening?
Well, I think that depends, of course, on, or from my side, I would say, yeah, for call sign highlighting, or that should be easy part, or yeah, maybe even integration with CPL DLC. Just so that the ATCO is not forced anymore to input everything with mouse and keyboard. He just talks to the assistant and then he clicks. Yeah, that's it. That could be an application, or I would say what the auto control people are doing at the moment, that they want to do it for radar label maintenance. They do not want to input everything anymore. Yeah, I think that will be the applications where you will have it. Of course, pseudopilot's replacement. Yeah, but I think that's in operation already.
Yeah. I think the data link application is a difficult one, because checking whether the recognition is correct would put the controller in a different cognitive mode than speaking. So it might be quite disruptive if he would have to verify that his speech was correctly recognized.
Yeah, let's see. But yeah, if you have direct to 00 west, 005 north, then direct 0008, or do you think the pilot can immediately do that? Well, maybe let's try it. Yeah, I just want to say that, because I expect always the argument, well, we soon will have CPDSC. Why you have speech recognition? Yeah, no, I think they can coexist for a long time. And maybe you know, ES Avia is one of our partners in Hawaii. They already have 70% of their communication via CPDLC. And they want the speech recognizer. They want it for the rest.
Okay. And maybe a little more provocative, if we think back about the plenary debate we had this morning, multimodality, why does it take so long? I remember speech recognition is something we've been working on for quite some time. And we always had this, well, I had, and I think you too, this carrot in front of us. Yeah, it's only 1 or 2 more research projects away. It takes another 5 years, and then we will see it in reality. But we seem to have underestimated the difficulty. So why does it take so long, Hartmut?
Well, I think because people are thinking it's so easy. Yeah, because how many projects you have now in ATC who want to bring this into the ops room? We have a lot of research projects, but nobody is using this approach of Hawaii or of Mallorca. Everybody tries to do it by himself. Why? Yeah, and then after 3 years of project, they see, oh, we only achieve 70% of recognition rates. I think that's maybe the problem. I think it's ready for use. We have shown it.
Yeah, it is shown in a SESAR project. Remind me, PJ 1604 or something like that. And wouldn't that have been enabling a more widespread use of it? Have you seen that? Have you seen an uptake?
No, I think the problem of 1604 was there were 5 speech recognition applications running with the best had a recognition rate of 80%. But in research, we already have shown on real ops room data that we have 90%. So why not using this output of research? Do it, use it. Don't try to use all those American approaches.
Okay. Excellent. You're off the hook, Hartmut. Thank you very much.
Okay.
And you stay on because I would like to encourage the audience to post their questions into the Q&A. I don't see any there at the moment. If you have questions, don't hesitate, put them into the Q&A. Please also type the name of the person whom you would like to ask that question, Hartmut or Matthias or Yash or Tiago. And I will now hand the floor to our second speaker. And the second speaker is Matthias Kleinert. He's a computer scientist who graduated from Braunschweig University, and he joined DLR afterwards. He's working in the area of machine learning, specifically in automatic speech recognition. And I look forward to asking Matthias, why does it take so long? Now, he actually makes an interesting approach to speech recognition, and that is how can a commercially available speech recognizer be used in the ATC area? And I look forward to hearing the answer. Matthias.
Thank you, Dirk. Hi, everyone. Thanks for the introduction. The talk from Hartmut, which you have seen before, focused on how to actually measure the performance of a speech recognition system in the air traffic control environment. And as Dirk mentioned, this talk, on the other hand, is more looking on how to maybe easily get a speech recognition system which performs well in an air traffic control environment. But let's maybe just take a small step back first. Speech in general is, of course, a very important means of communication for mankind. Every day, every hour, every minute, we transmit quite a lot of information just by using speech. And speech, of course, also plays, as we have seen, a major role in ATC. Communication between air traffic controller and pilot primarily consists of instructions, reports, and readbacks, which clearly indicate what a pilot is going to do and how an aircraft is actually going to behave in the near future. So it seems like ATC speech contains quite important information. However, knowing that to this day, as I said before, the majority of ATC communication is not really being recognized and understood automatically as maybe an input for other tools or other systems. But what is the problem? Why are we are not just doing it? Why not just take any speech recognition system, a system like the popular systems from Amazon or Google, for example? Well, if you have tried it or if you want to try it, you will quickly realize these systems are not really suitable for ATC speech. Not because these systems are bad, they were basically created for a totally different purpose and not for ATC speech. And of course, other approaches exist and have been tried as well. The PJ1604 project was already mentioned, which used a commercial off-the-shelf speech recognition engine, but combined it with an already adapted air traffic control grammar for speech recognition. But still, the system in the end only achieved recognition rates between 31 to 82%. Custom research solutions exist as well, like the ones from Levenstein and Mallorca, which introduced ABSR, which achieve quite impressive recognition rates of up to 95%. But often these solutions have a little bit the problem that it seems like the speech technologies behind it are not easily transferred to the ATC industry, because you quite need a good amount of speech recognition expert knowledge. So the question often occurs, is an easier solution maybe possible? And if you look at what has happened in recent years, you have seen that, for example, end-to-end speech recognitions have become quite popular, which already dramatically simplifies the training process for speech recognition systems. But that leaves the question, if it's easier, does it mean it's also usable for non-speech recognition expert? Could non-speech recognition expert train these systems? And if yes, does an implementation exist, which is maybe mature enough and also easy to use for everybody? And that's what I want to try to talk about in the remaining time of this presentation. In a short moment, I will show you a speech-to-text engine called Deep Speech, which we used and try to adapt it to the ATC environment. I want to show you what results we got with that engine. And I would want to talk about, again, what understanding speech actually means and how well we can understand speech based on the output that we get from the deep speech system. And in the end, of course, a short conclusion of my talk. So what is deep speech? Deep speech is an open source speech-to-text engine developed by Mozilla. It's originally inspired by a research publication from Baidu. And the input in the speech recognition model is, as always in speech recognition, features is extracted from a certain audio signal. And these features are input into a neural network-based model with overall 6 layers, 3 fully connected layers, then an LSTM layer, and then 2 fully connected layers again. And the output of the model is basically a probability of characters over time. So what this model is on its own able to output a recognized sequence of words, basically in the end. Nevertheless, deep speech additionally offers the possibility to add an additional language model on top of the neural network-based model just for the purpose of improving the recognition quality. And what is even more important, especially for non-experts, deep speech comes already with a lot of descriptions and tools which are easy to use to train a certain speech recognition model, to run the recognition itself, and also to prepare a model for deployment into production. So let's see how this goes. Let's use it to recognize ATC speech. So we looked at different training approaches and models and wanted to test them on ATC speech. The first thing is pretty obvious. We just used the already existing pre-trained English model, which comes with deep speech. It's already trained on around about 6,500 hours of data, which are publicly available. And the model has never seen any ATC related data before. We also wanted to train a model from scratch. So just throwing everything away, starting a new model, and just train it only based on ATC related data. The third approach is fine-tuning, meaning we take the already existing pre-trained English model and resume the training process on this model, but this time with ATC related data. We also used 2 other training approaches, which I will not really go into detail here. We also used transfer learning, which is more suggested to adapt a pre-trained model for a different character set. And we also used layer freezing, an approach which is usually used if you want to adapt an existing model to new languages. And as I mentioned before, deep speech offers a possibility to add an additional language model on top on all of these neural network-based models. So we additionally also trained some language models to combine them with the neural network-based models. So that was just a very rough, very quick description of deep speech and what kind of training approaches we looked at. Let's look at how well the system actually performed. So first, the data which we used for training, testing, and evaluation. We used data from different airspaces. So we used data from Zurich, Geneva, Vienna, and Prague with different controller positions, en route and approach. The data was recorded in simulated environment and as well as in operational environment. You also see here how the distribution is between male and female speakers and what kind of accent these speakers had. Overall, we used for our approach around about 33.6 hours of data, split it into three sets, a training set with 21 hours, a validation set with 9 hours, and a test set with around about 3.6 hours. So how well did the different models perform? Overall, we evaluated 12 different models combined with different language models. And the first thing we evaluated is obvious, it's the word error rate. It's the most commonly used metric probably for speech recognition system. And it more or less tells you how accurately your speech recognition system is able to recognize the inputted speech. I will not go into all the models which we've trained here. You can look it up in the paper if you want to. If you look at the pre-trained model, for example, which has not seen ATC data before, it's pretty obvious that this model does not work at all for ATC speech. If you don't combine it with an additional language model, you more or less have a word error rate of 100%, which basically means you didn't really recognize anything. If you combine it with an additional language model which of course has seen some ATC data. You get it down a little bit, but it's not really usable at all. In the end, with all the training approaches, the best results which we got came from the fine-tuning model. So using the pre-trained English model and adapting it with ATC-related speech. Without a language model, we got an okay word error rate of 15.5%. But with an additional 4-gram language model, we got down to a word error rate of 6.0%, which is from our point of view, pretty good and usable for an application. So I know you have seen it in Hartmut's presentation already, but I want to remind you of what we mean by that understanding is more than just outputting words based on a given audio signal. So natural language in general offers, of course, a lot of different possibilities to express a certain attention with a lot of different words. And also ATC is here not really an exception, even so the ATC phraseology is standardized. And here's just one quick example. Air traffic controller could say Lufthansa 3 Echo Romeo, make it heading 220 degrees left. Or he could abbreviate it a little bit and say Echo Romeo, turn left 220 degrees. He could also say this, or that, or even this. But in the end, it doesn't really make a difference, because in the end, all these different sentences have the same meaning. They all mean that the Lufthansa with the call sign 3 Echo Romeo should turn into the left direction onto a heading of 220 degrees. So what you want is, as Hartmut already showed, you want to be able to transform a sequence of words into clearly defined concepts which describe the meaning of these words. We used for that purpose the PJ1604 ontology. And luckily, we do not just only have the definition of the ontology, we already have an implementation which is capable of transforming this sequence of words automatically into these ontology-defined concepts. So that was just a short and quick reminder what I mean by understanding ATC speech. So what did we do next? We wanted to evaluate how good with our concept extraction we can extract the relevant concepts from the recognition which deep speech delivered to us. And for all the experiments you will see here, we only used the best model which we could train on our own. So we used the model which on average got a word error rate of around about 6%. And just for your information, the evaluation was only run on the Prague and Vienna datasets, because for all other datasets, no ground truth concerning conceptual commands was available. So there we couldn't really evaluate anything. Here, again, a small description of how the data looked like. We had operational data from Prague and Vienna and lab data from Prague and Vienna. And we had around about between 6,000 commands for most of the areas, and around about 2 commands per utterance were contained in each single file. The metrics we used were already described by Hartmut. We used, again, command recognition rate, basically meaning how many commands could be correctly extracted. We used command recognition error rate, so the opposite of that, basically. And we also looked at the call sign recognition error rate, so how many call signs were falsely recognized, which is, of course, very important, because if you don't recognize the call sign, everything else which you recognize does not really matter, because you cannot align it with any aircraft. Here are the results which we got. The gold columns always show you how good the extraction works if we input a perfect recognition, so a recognition which was created or verified manually, and which therefore has a word error rate of almost 0%. And besides that, you see the error rate here, for example, which we get when we use the automatic output from the deep speech model. And here we also put a little bit more detailed how the word error rate for the different data sets looked from the deep speech model. Here you can see, for example, that for the ops room data, the word error rate is relatively high compared to the lab room data. And if you look at the call sign error rate, if we use it on perfect data, the extraction is also almost perfect. Yes, if we use it on automatically extracted data, it goes a little bit down, but I would say it's still pretty good and usable. And the same is true when you look at the extraction of commands. Here again, the gold ones, and here the automatic ones, which of course have to deal with the errors which this deep speech engine makes. So let me just quickly conclude what we have done. We have trained various models with the tools which were provided by the deep speech engine. And from our point of view, the results are pretty good with a word error rate of 6%. The tools and scripts were for us very easy to use and very mature. Even so, we wouldn't consider ourselves speech recognition experts. Also, we have seen a language model is by definition not really necessary, but it's still, we could still show that it significantly improves result, in our case, for the fine-tuned model by a factor of 2.5 if we use a 4-gram language model. The results of the semantic interpretation showed that the word error rate, for example, quite varies for the different data sets between 1.1 and 9.1%. But if we want to get better models, improvement can be expected. The easy way is, of course, adding more data. That's always the solution. But here we just trained a general model, combining data from different areas to get one model. But you, of course, could, with enough data, also train a specific model for specific areas. And future work could be train at first a general model for ATC speech with a lot of different, from a lot of different areas. And when you want to use it for a specific area, fine tune it to the specific area. And we have also seen another project that context knowledge can improve the word recognition. So we should look for ways how we could maybe incorporate context information, which we could get from the surveillance data, for example, into the recognition process of deep speech. So I think I'm a little bit over time, but I hope that's okay. I'm done now. Thank you very much.
That's okay, Matthias, this time. And we don't have any questions in the Q&A, but I do have a few questions. I would like you to leave the conclusion slide up, please, if you can, because some of my questions will home in on what some of your bullet points. Now, the first thing is that comes to my mind is in its very architecture, the deep speech model seems to be quite different from traditional, if you like, speech recognizers with an acoustic model and a grammar and a hidden Markov model behind it and all the rest of it. It seems quite different. And I'm wondering whether this is the future. Is the architecture of speech recognition systems going to change? Or is this just a very exotic solution that is not going to influence the architecture?
So yeah, you're right, of course. If you look at the traditional, or let's say conventional ASR pipeline, the deep speech model is quite different, but it's not the only one of its kind. These kind of models, as I mentioned a little bit, I think in the beginning, have, I think in the last few years, become more and more popular because, well, it's a little bit like in all the area that have to do something with learning. These neural network-based models become more and more popular as soon as you figure out how to use them for a certain problem. So I cannot answer that question for sure, but I have the feeling that we will see more kind of these models in the future. And as I said, deep speech is not the only model who does it like that. I think the how it's called, the Web2Vec model from, I think it's from Facebook, for example. I think it's also an end-to-end model based on a neural network, and there are more out there. So deep speech is for sure not the only solution, and I think more and more are appearing.
Okay, so you think we might be seeing different architectures in the future?
Different architectures, yes, but I think most of them will be based on neural networks somehow.
Mm-hmm.
The deep speech architecture, if you look at other architecture, is quite simple, but as we have seen, it has proved to work quite well for ATC speech, at least.
Mm-hmm. And then slightly provocative, perhaps, and Hartmut, you can come in and shout at us if you want at any point. I mean, you're kind of doing, Hartmut, what Matthias, sorry, what Hartmut said you shouldn't do, and that is apply a commercial speech recognizer in order to solve ATC, whilst and I think with the word error rate of 6%, Hartmut's probably not going to be satisfied. So you're applying, and I applaud this, a commercial system to the domain of ATC. Is deep speech the way to go, or is it a project that showed we really need the research-based speech recognizers? Hartmut, you're happy? You're welcome to comment on this as well.
Matthias, you want to start, I think.
Okay, so let me start, and in case I say something wrong, you can intervene, I guess. First of all, I wouldn't really consider deep speech commercial off the shelf because, well, it's more or less an open source project. Yes, it comes from Mozilla, but other than that, everyone basically can participate and can have a look at the code, how it works, and so on. And what we did in the end, we basically trained our own model, let's say. So you can, from my point of view, adapt it to any area you like. It's a little bit different from what was done, for example, in the PJ1604 solution. Yes, they did adaptation, but they did not really adapt the speech recognition engine. They just injected into the speech recognition engine a grammar which covered ATC speech. So that's quite less than we did here. Training a new model, I would say, is a little bit more than just creating an ATC grammar. Or what would you say, Hartmut?
I would say the same, yeah, that we did not use commercial off the shelf here, yeah, that you of course also did, but then you end up with 100% of word error rate, where you just use the system which you got already trained on 6,500 hours. You completely adapted it to the ATC domain. Of course, you use the neural network approach and these models which were provided by deep speech. Yeah, I think it's just the framework which you adapted. And yeah, I'm completely happy, Dirk, with 6% of word error rate. If you get 5% of word error rate, I would say that's already nearly perfect. The rest must come from the understanding architecture. Even Apple is not going below 5%. That must be solved by the rest.
Mm-hmm. And maybe to give you an example that you really have influence and that you can change deep speech if you wanted to. I did not really mention it. This layer freezing training approach, for example, it does not come with deep speech. We found a publication which describes this approach, but if you want to use it, you have to implement it on your own into deep speech. It basically doesn't exist in the solution.
Mm-hmm. Excellent. I have two more questions, but I think we only have time for one. Can you go back to the last slide with the conclusions on it? And in the next steps, actually, you were suggesting to marry the system with context-sensitive speech recognition. And that is the approach, of course, that you followed in Mallorca and Hawaii as well. And I'm wondering whether you're planning to do this here when you say future work. Is that the way to go for deep speech to put some context knowledge into it? And if so, how are you going to go about it?
To be honest, to put context knowledge into speech recognition for ATC, from my point of view at least, should be the way to go for any speech recognition solution, at least for recognizing call signs, for example, because that knowledge is available and eases the recognition process a lot, because, well, I think I already said it quite a few times. When you look at what kind of call signs are generally possible without knowing anything, millions come to mind. But if you look at a certain air traffic control position, you have maybe 10 or something like that, which are actually under control of a certain air traffic controller. So the search space alone from this information can be reduced dramatically. And we have seen that in the research solutions, for example, which we did together with Saarland University and with EDIAP and with Beauty, for example, in the Hawaii project. So it should be included in any speech recognition application from my point of view. We don't yet have an idea on how actually to do that in deep speech, but I think it's for sure worth to look at it and figure out on how to do that.
Excellent. Thank you very much, Matthias and Hartmut. And since I've been preaching timekeeping for 2 days now, I think I cannot overrun, although I would be tempted to ask another question. We break for coffee now for 10 minutes. We're back here at 1600 sharp for another 2 interesting presentations. See you in 10 minutes. So Yash, he's a PhD candidate at the Air Traffic Management Research Institute at NTU in Singapore. And he researches machine learning applications, and specifically in the area of strategic conformance. So we look forward to your presentation, Yash.
Great. I'll share my screen now. Okay. I hope my screen is visible to all of you.
It is.
Thank you so much, Dirk, for the introduction. Hello, everyone. My name is Yash Guleria, and I'm a PhD candidate at the Air Traffic Management Research Institute. Today, I'll be presenting to you our recent work on a machine learning framework for predicting air traffic conflict resolution strategies for conformal automation. Before I start, I'd like to extend special thanks to the co-authors, Dr. Fu, Dr. Thin, and Professor Samir Alam from ATMRI, and they're in the audience, and Professor Nicolas Durand from INAC France, and also the air traffic controllers who participated in the experiments. So the flow of the presentation is as follows. I'll start with the motivation, why we wish to pursue the research on strategic conformance, specifically in air traffic control, which will be followed by the research question that we wish to address. Subsequently, I'll discuss with you the methodology, where we have 4 individual modules which are interacting with each other to obtain the desired results. Finally, I'll discuss with you the prediction results of the machine learning model, and it will be followed by some discussions on the results, and ultimately the limitations that our approach has currently, and the future works that we wish to extend. So the researchers have identified that with the increase in the aircraft in a sector, the perceived conflict rate increases exponentially. It has also been researched that with the increase in air traffic, the ability of the air traffic controllers to detect conflicts decreases drastically. So we can infer that even though air traffic controllers are a critical and very important component of the air traffic management system, the cognitive limit capacities will be a bottleneck in increasing the sector capacities. So there's a pressing need to identify ways in which we can increase the sector capacities, or to provide some assistance tools to the ATCOs through which they can better manage traffic. Now, even in conflict detection, the major limitation of the automation tools is the lack of human element, which is necessary for acceptance. Unfortunately, as for conflict resolution, currently there are no operational tools. There are no tools in operations as well. This brings us to the concept of strategic conformance. Basically, strategic conformance is degree to which the automation's problem-solving style matches that of the individual operator. Further, strategic conformance has basically two components. One would be in terms of the product or the output, and the other would be in the way that the output is achieved, which is the underlying strategy. So once these two components are achieved, then we can say that the automation tool has strategic conformance with the human operator. So in order to establish a parallel between strategic conformance and conflict resolution, I would like to share an example with you guys. So let us consider an example where the two aircraft are in a conflict in this sector, and the ATCO has a preference of maneuvering this aircraft in the form of this trajectory. Now, if an automation tool suggests a resolution which is different from what the ATC's preference is, we can say that in both the cases, the end product is achieved. That is, the two maneuvers achieve safe separation, but there is no conformance in terms of the underlying strategy. Whereas if a model 2 is able to suggest a resolution which looks similar to the ATC's preference, in this case, we might say that this automation tool has strategic conformance with the ATCO's strategies. We're also aware that air traffic environment is fairly complex with inherent stochasticity and the associated uncertainties due to delays, weathers, human operators, and machines. So it becomes very complex to accommodate these stochasticities in mathematical models. That is why we wish to approach this problem through a data-driven approach and use machine learning. Now I'll jump to the problem formulation. The problem at hand is to develop a machine learning-based strategic conformant automation tool for air traffic conflict resolution. Now this problem can be subdivided into three basic components. The first being, how do we identify the ATCO's strategies? Second, what is an optimal representation of those strategies in conflict resolution? So once we are able to represent those strategies mathematically or in form of feature vectors, then we can apply suitable machine learning algorithms. So finally, what is a suitable machine learning algorithm or a model which can predict those strategies? For the methodology, I have 4 different modules which are taking inputs from the previous modules. These are data generation, data analytics and visualization, feature extraction, and finally the machine learning model. I will discuss each of these modules in detail in the subsequent slides. For data generation, we used the Singapore FIR and specifically Sector 6 of the Singapore FIR with the airways included in the sector. For generating flight conflicts, we identified the intersecting airways and the conflict points. So once the conflict points were identified, we fixed the origin of the aircraft outside the sector, which was 20 nautical miles outside the sector. So then we knew what is the conflict point and what is the start point of the aircraft. So then we created offsets to ensure that there is always a conflict. So this was the way in which we generated the conflicting flight plans. Also, in order to ensure that the conflicts are similar and not exactly the same, there were certain offsets which were added to the flight plans. Offsets in form of the time of start of the flight. For the simulation environment, we've used the Escape Light simulation platform, which is the academic version of the Escape simulator by Eurocontrol. So in this image, we can see the radar interface, which the air traffic controller sees when he is performing the experiment. And here, this screen shows the input module of the air traffic controller, where the air traffic controller can input his desired maneuver preference for a particular flight. Once this exercise was completed and the data was collected, we obtained the original flight trajectories on the desired airways and also the maneuvered flight trajectories, which are shown in this image. Next, I'll move to the data analytics and visualization module. The data which was received from Escape is high fidelity data with a lot of parameters. But for our research purpose, we basically filtered out what we needed, which was the position of the aircraft at an interval of every 5 seconds. After this filtration, We clean the data to remove any outliers or missing trajectories due to runtime errors of the simulation environment. Once the data was cleaned, we could plot the trajectories obtained for both the ATCOs. So here, for each ATCO, we obtained almost 600 flight conflict scenarios. A visualization of all the conflict maneuvers is here. Through this, we were able to extract the strategies, which I will discuss subsequently. Before I discuss the strategies that were identified, I would like to share with you the representation of the strategies which we have. So basically, a strategy is a sophisticated planning skill which the ATCOs use in order to better manage the traffic and also preserve their cognitive skills or the cognitive capabilities. When we talk about a mathematical representation, a strategy is basically a sequenced tuple of the included elements. So here, C is basically the choice of aircraft to maneuver. T is the maneuver initiation time. D is the direction of the maneuver. What is the direction of the maneuver? Is it either left or right of the aircraft? DC is basically how far from the initial trajectory what is the aircraft deviated. And M is the list of the waypoints that are available after the maneuver initiation. So in this figure, we can see that at point P1, the maneuver is initiated for the aircraft. The aircraft is deviated to point P2, which is the point of maximum cross-track deviation. And then from here, the aircraft is merged into its initial trajectory at point P3. So this would incorporate the complete resolution profile of the aircraft. It is also important to understand that air traffic conflict resolution does not only include the initial maneuver, but the ATCOs are also responsible to merge the aircraft finally into the original flight trajectory. Now that we've defined the representation of the strategies, we can compare the two ATCOs data to evaluate what are the strategies in form of 5 components. So even when we just visually compare the two data sets, we can see that there is significant difference between the preferences of the two ATCOs. Specifically, ATC A prefers slightly delayed maneuvers when we compare it to ATC B. Now, in order to better understand the strategies, we compared the resolutions at each conflict point. For example, in case of the conflict at the waypoint Omlev, we can see that ATC A has very delayed maneuvers when compared to ATC B. ATC B has a preference for early maneuvers, and also the cross-track deviations seem to be relatively higher when compared to ATC A. In this case, the conflict point is Mumso, and we again see that there's a consistency in the direction of maneuver as well. So ATC A's direction of maneuver is always the region bound between the two aircraft trajectories. Whereas for ATC B, we can see that sometimes ATC B prefers a different direction of resolution maneuver. And also in this case, we see that the cross-track deviations are higher. But another interesting insight here is that for ATC B, there's a consistency in the merging waypoint. When we compare it to ATC A, ATC A has an option of choosing 2 different merging waypoints, Skilot and Mabal. So here we can infer that there might be some visual fixed points where the ATCs prefer to merge the aircraft in order to maintain the order of flow of the traffic. Similarly, in this conflict point, we can see that ATC B again has a preference of relatively earlier maneuvers, but with higher cross-track deviations, and we can see that the distance to the merging point is then obviously higher. Now, if we compare the data of the two ATCs, we can get the exact numbers in the form of this table. So ATC A, when we compare the data of ATC A and ATC B on the same conflict scenarios, in terms of numbers, we can see that the distribution of data for ATC A is less than 10 minutes. So basically, what this means is that ATC A has a preference to maneuver the aircraft late. I mean, ATC-B here has a preference to maneuver the aircraft relatively earlier. So for some data points, even 13 or 12 minutes prior to loss of separation, ATC-B would maneuver the aircraft. But on the contrary, ATC-A has a preference of delayed maneuvers. Similarly, for a cross-track deviation and the merging distance, we can see that the preferences of ATC-B are towards the higher end of the spectrum. An interesting finding here is in terms of the separations that are achieved by both the ATCOs. So in terms of numbers, we see that ATC-A achieves an aircraft separation after conflict resolution of 8.49 nautical miles. Even ATC-B has a similar separation achieved. These are the average numbers. So another inference that we can draw here is that the buffers that the ATCOs are keeping when they're performing resolutions. Now we shift to the feature extraction module, where the data set was curated into feature vectors, which would be fed into the machine learning models. So in terms of the features, we categorize the features into three categories, which are the conflict pair features, the surrounding environment features, and the resolution maneuver features. For the conflict pair features, we just compare the original flight trajectories. For example, in this case, we can evaluate what is the initial heading of the aircraft for both the aircrafts, what is the conflict angle, at what time will these aircraft experience a loss of separation. So basically, which aircraft is trailing or leading. Similarly, we can evaluate the resolution maneuver features, which would be our target variables. So here we are comparing the original flight trajectories with the resolved flight trajectories at every time step to find out, for example, when is the maneuver initiated, what is the heading angle, how far or what is the cross-track deviation, and what is the merging waypoint. So this way we can identify all the characteristics of a resolution maneuver. Now I'll discuss with you the machine learning model that we have adopted. Since the dataset was relatively smaller, for both the ATCOs, we had almost 600 conflict scenarios. So we used basically a 5-fold cross-validation because in smaller datasets, if you just extract the test set, it might not give us the holistic representation of the entire dataset. So we used 5-fold cross-validation and chain predictions, which I'll discuss with you now. So basically, the idea of chain predictions is the output of one model is used as input for the other model. So this includes the earlier defined features, plus the output of, for example, the first model here is fed as the input to the second model, and subsequently for the fifth model in this chain, all the predictions from the previous models are used. So this way, we are trying to predict all the components of a resolution maneuver profile. And from these predicted values, we can then reconstruct the trajectories. I'll now discuss the results of the machine learning model. So basically, the base model that we used was random forest in the form of random forest classifiers and regressor chains. Further, we used XGBoost and support vector machines. So the purpose of trying 3 different models was to evaluate if we could achieve better accuracy with the given data set. The only problem with human-in-loop experiments is the collection of data is extensively time-consuming. So we can see that our base model, the random forest model, achieves a significantly good results and lesser mean absolute errors in terms of the distance to maneuver, the CPA, the heading angle, the cross-track deviation, and the classification accuracy for the random forest model is fairly high. When we compare it to
2 minutes,
XGBoost,
please.
Sorry?
2 minutes.
Oh, great. When we compare it to XGBoost, the results are very comparable, but support vector machines are falling short in this regard. Another important finding is in terms of the feature importance. So given the two same conflicting data sets, the machine learning models show different preference of feature importance. So what we can infer from this is that since the strategies of the ATCOs are incorporated or encoded in the dataset, these different values of feature importance might be indicative of the different features that they consider important while resolving conflicts. Also, we see that the predictions from the previous models have fairly considerable feature importance values. So this validates the use of chained predictions for completing the resolution profiles. On similar lines, once we have the complete resolution profile, we can predict the entire strategy tuple. So in this way, we can compare the predicted aircraft trajectories to the original preferences of the ATCOs. And we can see that the predictions have a very close conformance with the original flight trajectories. I'll quickly conclude our findings. So the mean absolute errors and the accuracy of the models assert that the framework enables accurate predictions of the conflict resolution strategies. And the model predicted trajectories have close conformance with the original ATCO's maneuvers. I'll actually shift to the limitations of the work. So since this is a supervised learning approach, there are some instances when the assurance, conflict resolution assurance is not guaranteed. But for the cases where we achieve conflict resolution, the trajectories are very conformal to the ATCO's preferences. Another limitation is that the performance of the model was validated on the same set of scenarios, which was also highlighted by the reviewers. So we need to test the model performance on some different scenarios, some different conflict scenarios. So for the future work, we aim to address these two limitations first, and then increase the number of participants so that we obtain a holistic picture of the ATCO strategies. Also, there's a need to upscale the experiments to include secondary maneuvers and more complex traffic scenarios in our experiments. Thank you so much.
Thank you very much, Yash.
Wow.
I have a bunch of questions. I have to apologize first that the questions that are related to the speech recognition talks, that I picked them up so late. They just appeared in my browser when the session was already over. But I invite Matthias and Hartmut, perhaps if they want to type in some questions into the Q&A. That is possible. Now, you were referring yourself to some limitations in your work, and don't get me wrong, Yash, I think what you're doing is great, and you got to get started somewhere. But right now, you got started where it is relatively simplistic in terms of well, the conflict scenario that you were looking at. Predominantly, you can move one aircraft before or after the other, and you can do it early or late or so. In reality, when conflicts become more complicated and they involve multiple aircraft and other constraints like handover agreements and meteo and all the rest of it, I'm wondering whether the features, you will probably not have 5 features, you will probably have some sort of feature explosion that is very difficult to manage. Can you speculate about what's going to happen if your scenarios are becoming more complex?
Yes, so currently what we had in mind was to keep the features very generic in terms of the dimensions of the sector, so that if we use the similar approach at a different sector, the features remain relevant. But I am in complete agreement that once we expand the search to include other dimensions, for example, handovers and vertical maneuvers or different maneuvers, multiple maneuvers in the same conflict resolution, then there'll be definitely an explosion of the feature vectors that we have. So that is where we aim to use reinforcement learning, for example, zero-shot learning, where we can accommodate these kind of explosions of features. So right now the approach is fairly simplistic, and we're using supervised learning. So supervised learning in itself has some limitations. And I'm in complete agreement with you that there's going to be a definite explosion of features when we upscale the experiments. So we have in mind some approaches to address those concerns. Yes.
Mm-hmm. And following along the same lines, you have 2 participants at the moment, and you found a difference between their way of handling the same conflict, and that's great. I'm wondering, if you didn't have 2 but you had 20, would you have 2 camps a definite group of controllers doing it this way and another group doing it that way, or potentially would the conflict resolutions be all over the place and there would be no way at all to discriminate? Can you speculate about that?
Yes, this is a very relevant question actually. What happens if the thought process or the preferences of the ATCUs are very different? So in this direction, there has been research where the researchers are proposing individual sensitive automation. For example, if I have 5 controllers and 5 controllers have different preferences, so how can one model or different models learn from them? Can we create a mechanism? For example, if the first ATCU is on job, the model adopts to the ATCU's preference, and when for example the fourth ATCU is on job, how does the model adopt to those situations? So this is actually a very interesting question. But even if the ATCU's preferences, I would say, because the thought process is that because the ATCU's cognitive capacities are limited, they would not want to explore new ways to perform resolutions in a very packed sector. So they would definitely shift towards exploitation rather than exploration. And when we look at exploitation of the already existing strategies, then we can say that there are strategies which we can make use of. Otherwise, if there are no strategies and the system is completely random, then definitely machine learning approaches won't work.
Okay, thank you. And I think you're making the assumptions that controllers are consistent in themselves, meaning that one controller would always do kind of the same thing in the same situation, which isn't true. As past research has shown, controllers are quite inconsistent with themselves and would even contradict their own resolution advisories, which is a nice lead into the presentation that Tiago is going to give us about Mahalo. He might also speak about the predecessor project of Mahalo, which is called Mufasa. And I don't know. So thank you again, Yash. Stay around for the next presentation. Definitely. I don't know, Tiago, whether you managed to crank up your presentation. If you haven't, I have it here on my computer and I can share it. But
yes, try. Did it work now, perhaps?
Now, Sebastian in the chat has very helpfully suggested that perhaps you're on a multi-screen setup. And
yeah, I was, but I have changed that. Just let me.
All right. Well, if that doesn't work, I'll share it from my end if you want.
Yeah. Does it still not work?
No.
Okay. Could you share it then, please, Dirk? I apologize for it.
Yeah, you just have to give me pointers to.
Yeah. So hello, everyone. I apologize for the technical difficulties. My name is Tiago Nunes. I'd like to first thank my co-authors, Dr. Clark Bors, Dr. Eric Jan, Dr. Carl Weston, and Dr. Brian Hilburn. They've all been participating with me in the Mahalo project, as Dirk has introduced. Next slide, please. Yeah. So I'll first talk a bit about the Mahalo partners, our rationale behind why we're talking about the human interpretable input to machine learning. I'll go over our approach, give you a brief overview of our supervised learning, reinforcement learning agents, as well as our resulting automation. I'll make a few comments about the current results we have, and I'll finish with some conclusions. Next slide, please. Yeah, so we currently, within Mahalo, we are consortium working on one of the Horizon 2020 projects. And indeed, it is a follow-up to the Mufasa project. So this project is together with TU Delft, CHPR, the Center for Human Performance Research, Lidköping University, LFV, and Dirk, can you go a few more forward? Yes, so also with Eurocontrol and NACNE, and yeah, Deep Blue, which are our project managers. Next one, please. Yes, and one more. Yeah, so, and one more, please. So the reason why we're here talking about this is because we've seen that there is a demand for increased automation within the ATC domain. And what we've noticed, can you go forward one slide as well? And one more. Yeah, so what we've noticed is that when automation authority and autonomy increase, we tend to see a decrease in acceptance of humans. So if you think about, for example, a full manual control versus a supervisory control versus a fully automated control, as the authority of the automation system moves forward and forward, we see the acceptance of the human ATCO of these solutions proposed by the automation go down. And obviously that is not ideal, because if we have this automation system that is amazing at coming up with solutions, but ATCO doesn't trust the solutions and doesn't accept them, then the system isn't very useful for us. It's not really doing anything. Next slide. Yes, so in Mahalo, we're exploring in this particular paper, we're exploring how to build machine learning. So basically, we start from a question that is, should we build automation that is conformal or transparent? So we're really interested in looking at both conformance and transparency. So conformance, as Yash already mentioned, is if the automation seems to match human strategies. And we say here seems to match because we can have an automation that is trained for that, or you can, as we had in Mufasa, sort of fake that level of matching. And the second thing we're looking at is transparency, which is if this automation's inner process is explainable to a human. And this is very relevant in AI and machine learning, because as most of you know, most machine learning methods are black boxes. We don't quite know what's going on inside. So it can be difficult to diagnose why a certain input leads to a certain output. And this leads us to our sort of 2x2 matrix, where we say we can have low transparency and conformance, and that would be a stupid automation because it's doing something strange that is not conformal to the ATCO, and it's also not providing an explanation. And we have sort of like a higher transparency where we would have peculiar automation, which would be different than the ATCO, but still provide some explanation. And we have our confusing automation, which would be something that replicates the ATCO, but does not give any indication to the ATCO of why it's replicating that solution. And of course, our perfect automation, which would be perfectly conformal and perfectly transparent. Of course, here, as has been mentioned, one issue with conformance is that ATCOs are not 100% consistent. So we can't really be 100% conformal with a system or a human who is not 100% consistent. Next slide, please. Yeah, so within Mahalo in this specific paper, what we're looking at is how to create this hybrid machine learning capability. So we want something that is able to resolve and provide ATM ATCOs with conflict resolution advisories. And we also want to develop a UI to foster the transparency. So for this reason, we have created a supervised learning model that learns with the controller how to become conformal, and a reinforcement learning algorithm that learns how to be optimal. And I'll give some comments on optimality further ahead. Our UI will then provide transparency on top of that, and we will manipulate these two variables of conformance and transparency during human in the loop simulations. So currently we're performing one of our simulations. They're broken down into two parts. In one part, we go to ATCOs and we have them solve conflicts and gather data to train our personalized prediction models. And in the second part, we actually expose them to a system that's being trained to be conformal to them and to a system that's been trained to just be optimal. And we compare those solutions. So basically what we want to do is come up with a framework to how to develop, how to build ML for ATM in particular, and hopefully for other fields in general. Next slide, please. Yes, so here you see the overall approach that we're undertaking. So we have an ATCO that is interacting with an ecological interface display. So this is something similar to a plan view display with some additions to it. From this, we extract traffic state information that is given both to our personalized prediction model and our optimized prediction model. We then have a switch, which we manipulate experimentally to choose one of them. And we also can vary the level of transparency. So either if we want to just provide the advice, some intention information, or some rationale, which will be some high level explanations. Next slide, please. Yeah, so our supervised learning model is handling our conformal data, a conformal model. And what we do is we have a Sector X air traffic simulator that is built here in TU Delft. And we have humans solve scenarios within it. We extract these scenarios, the information from these conflict scenarios, and we put them on a solution space diagram representation. We then use that data to train a supervised learning model. And on the right here, you see that during our experiment, what we have is this robot that is trained on personalized preferences and gives heading advisories to a human based on what the human has chosen before. Next slide, please. Yeah, so basically what we're going to do is we train a model on multiple conflicts that the ATCO has solved. We use that with our ATC research simulator, as I mentioned. And what the AI sees is actually a solution space diagram. Now, the reason why we use a solution space diagram and why this is called human interpretable is because what we want to do is foster transparency and foster understanding and acceptance. And our idea is that if we use the solution space diagram, which is a human interpretable representation as input, we are creating a shared mental model between the human and the AI, and that fosters their work relationship and increases acceptance. So that's one of the reasons we're looking at it. One added advantage is that the solution space diagram is a pixel representation, so it doesn't increase in dimension if we increase the complexity of the traffic. So we take that solution space diagram, we create a data set, and for the supervised learning model, we train it with an 80-20 split, and we try to get it to fit onto an ATCO's preference. Next slide, please. And for this, we use Google Tensorflow, where we basically have a network that gets SSDs as input, which you can see here represented, and outputs heading advisories. We use convolutional neural networks for this simply because they're the best at extracting image information. Currently, we have data from ATCO students here at TU Delft. This was our Sim1. And in Rome right now, we just finished collecting data from 20 different ATCOs, and we have close to 720 different conflicts solved. Next slide, please. So the next thing I'll talk about is our reinforcement learning algorithm, and here we have two different ones. This is our simpler one, which is a Q-learning for modified voltage potential. So what we do is we have this modified voltage potential algorithm, which is a deterministic algorithm. And we use reinforcement learning to optimize two parameters, which are look ahead distance and safety margin. Now, this is our less important algorithm that we just used, that we developed initially to get some preliminary results. So I'll go on to our actual algorithm. Next slide, please. And this, can you skip a few ahead? There, yeah, that's it. So this is Dpq Learning from demonstrations, which is what we actually use in the final experiment. And DQFD, the Dpq Learning from demonstrations, comes from the fact that the reinforcement learning tends to be data inefficient, which means that we need to do a cumbersome data collection process, which involves a lot of interaction with the environment. And also reinforcement learning has really bad initial performance because it starts out not knowing anything about the environment. So DQFD kind of works around this by asking how can we make a reinforcement learning agent that is both more data efficient and has a decent initial performance. And what we do is we use demonstrations. So next slide, please. Yeah, and a couple more. Yeah, so we use representative expert demonstrations. Now, representative in the sense that they have to be representative of the whole state space. So we want to have a wide variety of diverse actions. And expert demonstrations here could be something for a human expert or a simplified good enough algorithm. And in our case, we use a modified voltage potential simply because this expert demonstrations are purely to provide with a good initial policy. So they don't have to be perfect, they just have to be good enough. So again, next slide. What we define by a sample or demonstration is just a regular tuple, which is the state, action, reward, and next state of the system. Next slide, please. So the way we do it is that we collect demonstrations, again, through the modified voltage potential, we put them into a replay buffer, and there's a pre-training stage where the agent will learn simply from sampling demonstrations for k amount of time steps. So this is a value that we define based on the kind of target performance we want in the beginning. And at the end of this pre-training stage, we have a good initial agent. Next slide, please. Next one as well. Yeah, so basically what we have is that this good initial agent is then trained on actual environment data. So we have an agent that observes a state, chooses the action, performs it, observes the transition, and stores that transition. For the DQFT agent, the state is also represented by the SST to take advantage of that shared work domain. And next slide, please. Can you skip one more? Yeah, so, and again, every time we have a new transition, we store this into a replay buffer, we sample from it, and we use this to update our neural network. So this allows us to have both the supervised learning and reinforcement learning agents using the SST, which are human interpretable inputs. Next slide, please. Yeah, so the way we do demonstrations here, and I won't get into it much, but it's basically like we keep some demonstrations always inside the replay buffer, and we use some kind of prioritized sampling where at the beginning the system will sample demonstrations a lot, and then we'll start sampling its own experience more and more. Next slide, please. Yes, so regarding the reward function, and this is something that I alluded to earlier as to what defines optimality in our case. We did workshop this also in a previous moment within Mahalo, which is for reinforcement learning and for our optimal system, we have to define what is optimal for the agent. And this is hard to do because in ATC, it's very hard to say, okay, what's the optimal objective measure for what system is better? And we came up with some ideas, thinking about collision avoidance, extra distance flown, extra time used, fuel usage, and workload. So currently we only use the top three, which is collision avoidance, extra distance flown, extra time used, because they are more objective. And also because our models do not take into account fuel usage, and the workload is sort of hard to define because this is purely an agent that is concerned with the scenario itself. So it is here that we understand that workload would also be something that an ATCO would point to say that the solution is better because it generates less workload in the future due to less need of monitorization. Next slide, please. Next one. Yeah. And one more. Yeah, so basically, if you look at the resulting automation, next one, please. We have an ATCO that is observing, this is what we envision to be the full system. We have an ATCO that observes the automation. And next slide. And two more, I think. Yeah, and then this ATCO has two different agents interacting with him or her. A conformal agent that gives a solution that's close to what he or she would do normally, and an optimal agent that takes into account these more objective parameters to give a good solution. Next slide. Yeah, one more. Yeah, and then we are trying to figure out what is the best thing to have. Is it conformal, optimal, or both, or maybe neither? Next slide, please. So currently, as I mentioned, the results we have are sort of very preliminary in that we only have results relating to the machine learning agent implementation themselves, because what we really will evaluate is sort of the effects of these manipulations of conformance and transparency on both trust and acceptance, and that we can only do in our final experiment, which will be somewhere in January, the first one. What we can say is that currently we did conduct SIM2A, which is our pre-test, where, as I said, we collected 720 different conflicts from 20 different professional ATCOs. And I can also say that the scenarios we have designed have been somewhat appealing to the ATCOs, and we got some positive feedback on that. Next slide, please. So again, the pretest is underway. We found out that the ATCOs reacted to the scenarios positively. They find them complex, a bit unrealistic without being artificial. This is mostly due to one of the limitations where we had to limit to horizontal resolutions due to the SST. They also gave additional feedback on the interface itself, which we will take into account. And one of the things we were quite happy with is that the scenarios are complex to keep the ATCOs engaged, so no boredom has been reported so far. Next slide, please. And then again, thank you for being here with me. I just presented to you the overall approach we're currently taking within Mahalo. Of course, we want to have this sort of combination of SL and reinforcement learning agents to achieve both conformal and optimal performance, depending on what we're looking to do. Of course, what we want to do mainly is to study the effects of conformance and explainability, and that can only be done once all of the data is collected, all of the agents are trained, and we actually have our final pretest, our final experiment. And of course, that will be the human in the loop experiment that we will do somewhere in January. And of course, we have introduced a sort of human interpretable input here to try to sort of make automation and humans work better. Can you go to the next slide, please? Yeah, so some comments on future work. We do understand that this work has some limitations. One of it, for example, which you probably saw, is that we use a solution space diagram, and we only consider horizontal solutions, so only heading and speed control. That is, of course, somewhat unrealistic because in real world air traffic scenario situations, you want to have also the ability to do altitude controls. This is something that we manipulated because simply we needed to use it as simplifications for our work. Of course, we would also like to look at more complex traffic scenarios, and that is including altitude, but also weather and different air traffic patterns, which we again had to reduce to keep the sort of solutions within a certain variety, because we don't have a lot of time with ATCOs, so we are kind of limited in the diversity of solutions we can collect. And of course, we want to also expand this work to other interfaces, such as, for example, the travel space representation, because we want interfaces that include more complexity and more information about the system. So next slide, please. Yeah, and I thank you for your attention. Here you see my contact also, as well as our project manager's contact and the website. So if you have any questions that are not answered in this session, feel free to contact us, and we will try to get back to you as soon as possible.
Excellent. Thank you very much, Tiago. So present this so very well, despite all the obstacles that IT put in front of you. I have a few questions which are quite similar actually to the questions I asked Yash. The first one is about externalizability of your scenarios. I mean, the scenarios that you have been using, and I invite the participants to read your paper where you describe them a little more. They are somewhat simplistic in the sense that it's relatively simple traffic scenarios with relatively simple conflicts. Now, I'm wondering whether once you are trying to address more complex situations with more than 2 aircraft involved, perhaps, and a number of constraining factors, whether conformance will remain numerically manageable, or will it just explode in complexity?
Yeah, that's a good question. And indeed, I would have liked to also go into our scenario design, which is something that we spent a lot of time on, but of course, presentation being time limited. Well, that is indeed, as I said, a good question. What we do know is that, of course, more complex scenarios will lead to more complex solutions, perhaps, and that will probably have an effect on conformance. We had to somewhat limit the scenarios to be somewhat more simplistic, also because we don't have a lot of time with the ATCOs, and we really want to look at the effects of conformance and transparency. We have to design scenarios that are approximately complex among each other, so that we also don't have differences due to just the scenarios themselves. So indeed, it is sort of maybe unrealistic and simplistic scenarios that were being used. And I can't give you a proper answer on what the effect would be. But that is an issue that we're aware of, that they are sort of scenarios that maybe are not unrealistic, but of course simplistic, and that there would be way more complex traffic patterns within a real world application. So that is something that we're aware of, but sadly it's just a limitation of the time we have with ATCOs and the systems we're using that we couldn't look into them.
Mm-hmm. And the other question is your approach, of course, requires that controllers are sufficiently consistent with themselves, but sufficiently different between themselves, right? In order to be able to quantify conformance, you need to have different controllers taking different approaches. And I think you were doing studies in Rome and in Stockholm. Maybe the Stockholm tests haven't taken place yet. Could you speculate a little bit about how different controllers from different centers or from the same center between themselves are, and does that allow instrumentalizing conformance?
Yeah, that's also a good question. So indeed, we want ATCOs to have a sort of a variability between them. And of course, that would be ideal, but we also want them to be conformal. I can't really speculate yet because we're still in the analysis of the data, the degree to which we expect different resolutions. Of course, we're limiting ourselves to only en route ATCOs. So we hope that will sort of bring down the variability a bit. But of course, it could be that we have ATCOs from Stockholm. We also have ATCOs from Rome and Padua. So it could be that they do have different strategies just purely due to their experience in different sectors and with different traffic patterns. So it's sort of like something that will likely pop up. But at the moment, I don't have enough data to be able to tell you the degree to which that variability exists.
Okay, thank you. And the last question I'll take from the Q&A stack. It's a question by Ender. I'll just read it out. I assume it is to you, although it doesn't have your name on it. Do you need to optimize more hyperparameters for DQFD method, especially the parameters related to losses weights in DQFD?
Yeah, so that is something that I couldn't get into, but you can read that on our paper. We did have to go through a hyperparameter tuning optimization stage, which is just common among all machine learning methods. So indeed, one of the things that we looked into was the loss due to the, well, specifically the pre-training stage. But we were not concerned with achieving an optimal pre-training stage. So our goal for DQFD is to have an agent that when it starts interacting with our ATM simulators already has a degree of good enough performance. So we could have tweaked it a bit. We could have looked into those hyperparameters a bit. What we really want is just what we really were looking for is just a reinforcement learning agent that is able to solve all of the complex that we throw at them and that we will have with the ATCOs. So there maybe will be some areas of training that could have been done better, but really for the level of, for the degree of detail that we need, we went through a hyperparameter training stage that was just enough to get the adequate performance we're looking for. So I'm not sure if that answers your question.
Okay, excellent. Well, thank you again, Tiago. Thank you also, Yash, Matthias, and Hartmut for these interesting presentations. We'll wrap it up here. And I hand the floor to Bram, who will show one teaser video of 1 minute and 30 seconds, I was told. After that, grab a cup of coffee and I'll see you back at 5:15 for the SITS quiz.
Iberia 3340, muy buenas, contacto radar, vuelen por la derecha, Crisa, ascienda en 350.
Gold Delta Kilo 27 Charlie Alpha, contact Barcelona 132.355, bye.